Hello to the fifth lesson of 6 on applications of forces. So far I've done loads of work with static problems. We've got particles resting on planes, particles in limited equilibrium, rods and ladders in equilibrium. But we've not really done much, if anything, on dynamic problems with moving particles or objects. But now we are going to. So this is what the focus is going to be on today. It's also a nice return to some SUVAT problems from year 12. But you'll see as we go through these together. For now, as ever, I want you to try some of these warm-up questions for me, 2 in total to be precise. So pause the video here, have a go yourselves, and then when you're ready to see what the solutions are, press play and I'll do my best to guide you through them. Let's have a look then together at question number 1 of this warm-up. So here we've got a particle of mass 1.5 kg moving on a smooth slope, and it's being acted on by a force of 4 newtons parallel to the slope as shown. The slope is inclined at an angle of alpha to the horizontal, where tan alpha is 0.75. Find the acceleration of the particle. I've mentioned this a few times now, but if you're given an angle in terms of a trig function rather than an exact angle in degrees, think of it, if possible, as a trigonometric ratio. So here we're talking tan. So tan alpha 0.75, that's 3/4. And tan is the ratio of the opposite side to the adjacent. So for every 3 units on the opposite side, we've got 4 units on the adjacent. That tells us, using a Pythagorean triple, that this one here, hypotenuse, will be 3 squared plus 4 squared, square rooted. 3 squared plus 4 squared is 25. Square root of 25 is 5. So this tells us that therefore sine theta, opposite over hypotenuse, that'll be 3/5, and cos theta, adjacent over hypotenuse, will be 4/5. So now finding the acceleration of a particle. So the particle is going to be going up or down the slope. Therefore it's a good idea to resolve going either up or down the slope. So it's going to have a weight. Its mass is 1.5 g. Sorry, its mass is 1.5 kilograms. So its weight will be 1.5 g, which we can now resolve going perpendicular and parallel to the slope. So you'll have a perpendicular component and a parallel component. We can now use what we've found, what sine theta and cos theta are, as exact ratios in resolving this appropriately. So we need to know that this angle is going to be alpha as well. You had plenty of practice with that idea, I'm hoping. So this component will be 1.5 g sine alpha. This one will be 1.5 g cosine alpha. But because we know what cosine alpha and sine alpha are in exact forms, we can replace this with an exact multiple of g. So 1.5 g cosine alpha, 1.5 multiplied by 0.8, that gives us 1.2 g. And here 1.5 g times sine alpha, if I do 1.5 multiplied by 3/5, or 0.6 for decimal equivalent, I get 0.9 g. Now there could be a force going up the slope, there could be a reaction, which of course there will be. But the thing here is we don't actually need to worry about what the reaction is, because there's going to be no acceleration in this direction, and we're told that this slope is smooth. So all we need to do now is consider forces acting parallel to the slope. So we need to ideally think about a direction which is going to be positive. So you might be thinking this 4 Newton force will push this upwards, so the acceleration is going to be going in this direction. So maybe you want to think that going upwards is positive, and that's fine. So the total of the forces going up is just obviously 4. We have this component of the weight acting against, which is 0.9 g. So the overall force going up is 4 subtract 0.9g. So 4 minus 0.9 times 9.8 gives us minus 4.82. So what does that mean? Well, that means that although this force is pushing the particle up the slope, it's not sufficient to actually stop this particle from sliding down. So it'll just go down the slope. This 4 Newton force will just make it accelerate at a lesser rate, but it will still be actually moving down the slope, which is quite counterintuitive. So therefore what this means is 4.82 newtons resultant force down the slope. Now we can apply the idea of F equals ma. And so 4.82 newtons, just taking the magnitude of a resultant, will equal the mass times acceleration. So that's for mass 1.5 multiplied by a. I'll say here I'm just using F equals ma in case you're wondering where this is coming from. Magnitude of resultant force 4.82, for mass 1.5, acceleration what we're trying to find out. So therefore the acceleration of this particle is 4.82 divided by 1.5. Let's see what that gives us. We get to three significant figures, 3.21 meters per second squared. Let's now have a look at the second warm-up question. So this one here is a particle suspended by two strings. Well, we've got a string AC and another section of a string going from C to B. So like I said, it's just fixed at A and B. The particle is hanging in equilibrium with AC and BC inclined to the horizontal at 30 degrees and 60 degrees respectively. So that's been given. Now, the tension in AC is 50 newtons, so I'm going to add on here 50, and we need to find the tension in BC, which we're not told, so I'm just going to add in that and call it just T. I could call it T subscript BC, but because this is the only tension we're trying to find, there's not much ambiguity. We can just leave this as T. Now, W for weight will be acting down, obviously. Firstly, to find the tension in BC, what we could do is resolve the components of forces going horizontally, because it's going to be in equilibrium. So this 50 Newton tension will have a component going vertical and horizontal, which I'll just fill in for you now. You should have had practice of me doing these before, but if not, take this as a chance to just run through these ideas again. So, the component opposite to the angle, in this case the component going upwards, is always a hypotenuse, or magnitude of the force multiplied by sine of the angle. So that's 50 sine 30 going up. Going along is 50 cosine 30. For this tension, the opposite component to the angle will be T sine 60. The horizontal component will be T cosine 60. So if we just think about the components going left or right, then the components going to the left, just for 50 cosine 30, that must be equal and opposite to the component going to the right, which is just this T cosine 60. Therefore, if we divide both sides by cos 60, T is 50 cos 30 divided by cos 60. So 50 cos 30 divided by cos 60. That gives us 50 root 3, which is approximately 86.6 newtons. And for part B, for value of W, we can now consider forces going up and down. Because it's in equilibrium, for forces going up, or components of forces going up, will be equal to forces going down. So therefore the weight, which is the only one going down, will equal 50 sine 30 plus t sine 60. Now we just worked out t from before, so we can leave t in our calculator so we don't need to round or remember anything awkward. So there, t is 86.6, so that's our stored answer, look. So here I can just type in 50 sine 30 plus that answer multiplied by sine 60. And what do you know? It drops out to be exactly 100 newtons. Isn't that nice? So, let's get started with some questions on dynamic systems. Dynamics and inclined planes. Very simple piece of knowledge is when a particle is moving along a rough plane, the force of friction is equal to mu r and will always act so as to oppose the direction of motion. So, let's have a look now at a worked example. Goodbye advice, bring on the example. So we've got here a particle held on a on a rough plane which is inclined to the horizontal at an angle alpha. Again, this tan alpha business being 0.75. So it's an incline. So let's just draw this on now. Whoops, wrong arrow type. Okay, so imagine the particle being there. That's alpha. Like I mentioned for the warm-up, we can just remind ourselves of what sine, cosine, tangent will be. Now we know what tan alpha is. Tan alpha is that's the same as 3/4. So the ratio of the opposite to the adjacent is 3 to 4. Using Pythagoras, this one will be the square root of 3 squared added to 4 squared, which will be 5. So therefore, sine alpha will be the opposite, 3, over the hypotenuse 5. Cosine alpha will be the adjacent, 4, over hypotenuse, which is 5. So that might come in handy later on. So we're told the coefficient of friction. This particle has been released and it slides down the plane. So because the friction will always act to prevent motion or act against it, we know the friction will be acting that way and will be limiting friction. So the friction is going to be mu r. Now mu is 0.5, so we can add that in. So it's going to be 0.5 r. Whatever this normal reaction is, which we can add in now, like so. Now, if it's sliding down the plane, that's because there's going to be a component of the weight going down the plane. So we can add in the weight. Now we're not told the mass, so I'm just going to leave the mass as m. So that's mg. Now we can resolve both perpendicular and parallel to the plane. So if that's alpha, this will also be alpha, which you hopefully should know. The opposite component is going to be mg sine alpha, and that's going to be mg cosine alpha. But because we can now deduce what sine alpha is, it's 3/5 or 0.6. mg sine alpha is mg times 0.6. That's just 0.6 mg going down the slope. Similarly, cos alpha is 4/5, so 4/5 of mg is just 0.8 mg. So now we can think about what the normal reaction is. So if we just consider, the acceleration is parallel to the slope. There's no acceleration perpendicular to the slope. So the forces are going to be balanced in this direction. So therefore the reaction going perpendicularly from the slope up will be equal and opposite to this component of the weight going perpendicularly down from the slope. So R will equal 0.8 mg. So therefore the friction, F max, will equal 0.5 multiplied by R. R is 0.8 mg. 0.5 times 0.8, don't have a calculator if you want, that'll give us 0.4 mg. So we can now consider forces going parallel to the slope. So for A, just think of forces going parallel to the slope. So forces going down, we've got 0.6 mg. Subtract from that forces acting up, which is this resistive friction of 0.4 mg. That gives us a resultant force of 0.2 mg down the slope. Now we can apply F equals ma. So resultant force is 0.2 mg. That'll equal the mass of the particle, which we don't know, just call it m, multiplied by the acceleration, which we're wanting to find. Now, wouldn't you know it, the masses cancel, the acceleration is therefore independent of the mass. Therefore A is 0.2 g. So g is 9.8, so 0.2 multiplied by 9.8. That gives us 1.96 meters per second squared. So 1.96 ms minus 2 down the slope. My handwriting gets worse and worse. Now B is a throwback to good old Suvat days. So we can assume that this slope is constant, this friction is constant at its maximum, therefore the acceleration is constant. If we're talking acceleration being constant, we've got the Suvat formulae for constant acceleration. So the distance it slides in the first 2 seconds. Let's wheel out Suvat. So the time frame is 2 seconds. We know the acceleration down the slope now is 1.96. We want to know the distance covered, so I'm going to put a question mark over distance. It was released from rest, so the initial speed was 0. The final velocity we don't know, and we don't want to know it, so put a cross through that, we don't care. So which of the Suvat formulae doesn't involve v? We don't know v, we don't care about v. So which one doesn't involve v, but does involve s? It's the good old s equals ut plus 1/2 at squared. So the distance covered in the first 2 seconds. Ut is 0 because u is 0, so I'm just going to have a half multiplied by the acceleration, which is 1.96, multiplied by 2 squared, which our calculator will kindly do for us. So 1/2 multiplied by 1.96 multiplied by 2 squared gives us 3.92 meters. And that's it for the first worked example. Second worked example, we have a box of mass 2 kilograms being pushed up a rough plane by a horizontal force magnitude 25 newtons. So the plane is inclined to the horizontal at an angle of 10 degrees. So already I'd be suggesting we can start sketching this out. So it's on an incline. The incline's 10 degrees, so it's fairly shallow. You don't need to draw the angle accurately, of course. It's a box. Let's do this as a particle. I'll put the box here. Don't need to draw it even as a box shape, just draw it as a blob. So it's got a mass of 2 kilograms. That means it will have a corresponding weight, of course, as anything with a mass will in a gravitational field. So that's going to be a weight of 2g acting vertically down. The incline's 10 degrees, so I'm going to label this on like so. And I'm also going to sketch in where I'm getting this information from. So if you're watching this back or I'm talking too fast, hopefully the colour coding will help you make more sense of where this information is coming from. 2 kilogram mass, hence 2g. And it's being pushed by a horizontal force of magnitude 25 newtons. So I'll add in this force in a red line, something like this. So it's straight on and has size 25 newtons. As well, it's a rough plane, so there's going to be friction involved. And friction, because it's a moving box, the friction will be F max. Because it's moving, you need to work out F max, which is the coefficient of friction multiplied by the normal reaction. The normal reaction is always perpendicular to the surface, so we can add this in like so. Normal reaction is going up perpendicular to the surface, like so. And so to find the normal reaction, we need to find the corresponding counterforce, which will be the perpendicular component of this weight. So if I just add in the components of a weight in a different colour, maybe a dotted line, like so. And of course we need to remember, if this angle's 10, this angle here will be exactly the same thing. Then the component opposite to the angle we know will be the hypotenuse multiplied by sine of this angle. So the opposite component of a weight, the component going parallel and down the slope, will be mg sine of the angle, whereas a component going adjacent here will be mg cosine of the angle. So there's going to be no acceleration perpendicular to the plane. Okay, it's fair to say that this box isn't going to fly off going vertically up, nor is it going to fall through the ground for some spectacularly miraculous reason. So we can say that the reaction force must balance exactly with the forces acting downwards. And that'd be tempting to think the only force acting down is this component here of weight, mg cosine 10. But actually, because this force here is horizontal, this too will have a component going parallel to the plane and perpendicular. So what we're going to do now is resolve this one. So we're going to resolve parallel and perpendicular to the plane, like so. Now, using some GCSE Z angles, we can hopefully, I'm hoping you can see, that from here to here to there makes a Z. In other words, this angle here is going to be 10 degrees, just like this angle there was 10. And because of that, resolving in the same way, the opposite component, like I said before, is magnitude multiplied by the sine of the angle, so 25, whoops, what's happened here? I think my pen's just freaked out slightly, apologies. That's going to be 25 sine 10, whereas this component will be 25 cosine 10, acting up the slope. Now I think it's fair to say we're fully labelled. That's as labelled as we need. So now we can work out the maximum friction. But first of all, we need to work out R. And so if we consider forces going perpendicular to the slope, forces going that way, they'll be balanced. So therefore R, which acts perpendicularly up from the slope, will be equal and opposite to the components acting perpendicularly down from the slope. So R will equal 25 sine 10 plus mg cos 10. And in fact, what I'm going to suggest we do here, I don't know what I didn't do before this, to be fair, I'm going to suggest we just call m 2, because it is 2. It's a force of habit of mine to put mg, but you know, I could, and probably should have just filled it in with 2g, because the mass is 2. So apologies for that if you're thinking, why did you put m when we know it's 2? Good question, I don't know what I'm thinking sometimes. So R will be 25 sine 10 plus 2g cosine 10. So we know what G is 9.8, so we can actually evaluate this reaction force by using this calculator. So the reaction, 25 sine 10 plus 2 times G, which is 9.8, multiplied by cosine 10, that's going to give us approximately 23.643, and so on and so on. Now this isn't a final answer, so what I'm going to do is I'm going to write this out in its entirety, just to make sure we don't have to worry about rounding anything off too soon. So 0.643, and then we had 4364. So therefore F max, which will be mu multiplied by R. Well, we're told what mu is. We've been told, if you look carefully, that the coefficient of friction in the box of the plane is 0.3. So it's going to be 0.3 multiplied by that reaction force we've just worked out. So 0.3 times this 23.643 horrible looking number. So do that, what do we get? So times that by 0.3. You get 7.09303 and so on. So 7.09303. What else did we have? 0.92 newtons. Now it's fair to say this needs labelling on as well. The frictional force exists, it needs labelling on, and it will always resist the tendency of the direction of motion. So here it's been pushed up a rough plane. So the motion is actually going this way. That's the motion and the acceleration. So this friction force, F max, will actually be acting down the slope and will be opposing the motion. So what I'm going to add on here is an arrow going down the slope like so. I'll call this here F max, which of course we've worked out which is a bonus. So we can now consider the acceleration of this box. The acceleration is going to be up the slope. So consider forces parallel to the slope. I'm going to say up the slope as our positive direction. As long as you're consistent, you can take down the slope as positive if you want to, but I suggest to do the direction of acceleration or motion as the positive direction. So going up the slope, the force we have, the component of the force we have, is 25 cosine 10. So the resultant force going up will be the 25 cosine 10 but now resisting that we have F max, so we need to subtract from that the limiting friction, which is 7.093 blah blah blah, because that's going to oppose the motion. And also going the opposite way to the motion is the component of weight going down the slope, which is this 2g sine 10. So we also need to subtract 2g sine 10. So overall, the resultant force acting up, we can work out here. So this stored answer, I'm going to leave as it is, because that isn't rounded, so we don't need to type it all out again. So this here is F max. So the resultant force acting up the slope is 25 cosine 10 minus F max, that number stored in our calculator, minus 2 times 9.8 times sine 10. And that gives us a value of 14.12 or so. Again, we can leave that number stored in our calculator. That's the resultant force going up. We can now use Newton's second law, which states that the resultant force is going to be the mass of an object multiplied by its acceleration. So the resultant force we've worked out is 14.12. That'll equal the mass of the object, which is 2, multiplied by the acceleration, which of course is what we're trying to find. So therefore, as a final step, the acceleration is going to be 14.12, etc., etc., whatever that awful number was on the calculator, divided by 2. So if we take this and half it, we get 7.06 to 3 significant figures. And that's the acceleration going up the slope, and therefore that is our final answer. Let's now have a look at question 3, which I've taken from a past paper from way back in the day. If you're watching this video, it might even be from before you were born. So, if you're wondering, well, here it is. So we've got an above diagram showing a boat B of mass 400 kilograms. So I'm going to label as I go here. This is just modelling as I would if this were a test scenario. So I'm been told it's got a mass of 400 kilograms. That means its weight is 400 G going straight down. It's at rest on a slipway by a rope. It's been held by this rope here. It's modelled as a particle, and the slipway is a rough plane inclined at 15 degrees to the horizontal. The coefficient of friction is 0.2. I'm going to highlight that. That's going to be used later. That's crucial information. The rope's model is a light, inextensible string parallel to a line of greatest slope of the plane. It's in equilibrium and on the point of sliding down the slipway. So it's about to slide down. That means there's going to be friction, which will be at its maximum because it's just about to slide down. So the friction is going to be limiting and at its maximum. Friction always acts to resist the tendency of motion. So in this case, the friction will be acting up the slope here, and I'm going to label this as F max going up. We also need to find the tension in the rope. Now tension acts away from objects, so for tension I'll go this way. I'm going to label that T for tension. We're talking about friction here as well, as you can see. So friction, maximum friction, is based off mu, which is going to be 0.2, multiplied by the normal reaction force. Now the normal reaction force will be acting perpendicularly away from the plane, something like this. So I'll label that R. So I need to find R in order to work out F max. But to find R, which is going in a perpendicular direction to the plane, that means I need to resolve forces perpendicularly and parallel to the plane. So that's telling me already that I need to be resolving this 400g weight perpendicular and parallel to the plane. So we can do this now. So perpendicular and parallel. Because this is 15 degrees here, I also know this is 15 degrees over there. The component of weight opposite to the angle is always the magnitude of the force multiplied by sine of the opposite angle. And the component of the weight going adjacent, in this case perpendicularly down, is 400g multiplied by cosine of this angle. And as well, F max is acting up the slope like so. And so we're pretty much good to go. So calculate the tension in the rope. So what we need to calculate first, if we can, is this normal reaction force R. So let's consider forces acting in the direction which is perpendicular to the slope. So going up and away, we've got R, and acting against R is this 400g cos 15 force. So R must be equal and balanced with 400g cos 15. So we can work out what R is. Because we know G is 9.8, so 400 multiplied by 9.8 multiplied by cosine 15 equals 3786.429. 3786 and 0.429239. Again, I'm not rounding yet because this is by no means our final answer. 429329. Good. So therefore, F max which is mu times R. Well, are we told what mu is? Well, actually, yes, we are. We were told the coefficient is 0.2. We've worked out R just now. So this is going to be 0.2 multiplied by that horrible 3786 number we just had earlier. I can't even be bothered to write it down. I couldn't even if I wanted to because we run out of space, as I always do. I never learn. So multiply the value we just got by 0.2, and we can see here that's going to be 757 point whatever. So 757.285 8478. So we know what F max is. So now we know what F max is, which is this horrible looking force here. We can now begin to think about the tension in this rope. So now what we can do is consider forces acting perpendicular, sorry, acting parallel, I mean to say, to the slope. Forces acting this way. So right now it's in equilibrium. So the forces going up the slope will be equal and opposite to the forces going down the slope. So as we can see here, the forces going up the slope, we've got the tension, as well as that we've got F max. For F max we worked out was this 757 point blah 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 number, because it just goes on and on. So the sum of the forces going up for tension plus Fmax must be equal and opposite to maintain the equilibrium to the forces going down the slope. If any forces going parallel to the slope downwards is this component of a weight, which is 400 g sine 15. So therefore, if we rearrange this, so therefore T equals 400 g sine 15 minus 757.285 and so on and so forth. That's going to equal, well, I'll leave that number stored in A and S because that's useful. So 400 multiplied by G, which is 9.8, multiplied by sine 15, minus that stored answer, gives me three significant figures, 257 newtons. And that's for tension in the string. Great, so what's in store next? Well, next up, for part B, it says the boat's 50 metres from the bottom of the slipway, the rope's detached from the boat, and then the boat slides down the slipway. So now we need to calculate the time for the boat to slide to the bottom of the slipway. So this question here, we're going to have very much the same forces acting on this boat, but of course some forces are going to change. So what I'm going to do here is I'm going to start off with what we had before. So these are the forces we had before, but of course if this rope is detached, what will happen is the tension will disappear because the rope will disappear. So if this tension vanishes, we'll have something a bit like this. So everything else will be the same, but the tension will vanish because this rope is no more, essentially. So we can imagine this rope as just being cut off, like so. So it'll be this sort of system like this. So now the boat will be moving down, and remember, when there's motion, we can always model the friction to be at its maximum. So this is why it was a good idea to make a note of the exact value of the friction. Here's what it was from before. So now we calculate the time taken for the boat to slide to the bottom of a runway. So because the frictional force is constant, the slope is uniform and constant, the weight and this component of the weight is constant, we can therefore assume the acceleration is going to be constant. So what we can do here is apply good old F equals ma. So the resultant force down the slope we'll take down as being positive. The forces going down the slope is just 400 g sine 15. So 400 g sine 15 less the resistive forces, which is just for friction, which is a 757 job here. 28, etc., etc. That's going to equal the mass of a boat, 400, multiplied by this acceleration, which we're obviously trying to find. So all we need to do here is to divide both sides of this by 400. So therefore we can say the acceleration is going to be 400 g sine 15 minus 757 2, etc., etc., divided by 400. So what's that going to be? So 400 multiplied by g multiplied by sine 15 minus the massive friction, which is 757.2858478. Divide that by 400. And we get the acceleration is about 0.643. And again, I'm going to write this in exact form, or as exact as I possibly can do, at any rate. So 0.643, 212, 0225. So now, based off this, what I can do is use good old suvat, because this acceleration I can model as being constant. So bye-bye text, hello suvat. Constant acceleration formulae. We want to find the time taken, so I'm going to put a question mark over the time. That's what we want to find. Acceleration is this 0.643 job here. For final velocity, we don't know, we don't care, cross that off. It will be released from rest because it was at rest initially. It was being held just about by this rope. So if the initial velocity is 0, then s, the displacement till it gets to the bottom, is 50. It's 50 meters till it gets to the bottom of the slipway. So what we need here is an equation of motion which does not involve v at all. And once again, it's the good old s equals ut plus 1/2 at squared. So s, which is 50, u is 0, so ut is 0. So that gives us half multiplied by 0.643, blah, 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 t squared. So if we divide both sides by a half times 0.643, we see that t squared, well, in fact we can do this in one step, t will be 50 divided by the half of 0.643, etc. What makes t squared the subject? But because we want t, we have to square root all of this beast, and then we'll arrive at what we want to find. So, what we need to do here, we've got acceleration stored in our calculator, which we can use to our advantage. We don't need to round or do anything awkward at all. So we now can square root this awful thing, 50 over the square root of a half, we're going to call that 0.5, multiplied by the answer stored in our calculator, that 0.643 number, and then we get 12.468, etc. So that's approximately 12.5 seconds. And then finally, we're done, we're gold, big relief. So that's all we need. So now it's over to you folks. So what I'd like you to do, turn to page 148, exercise 7e, and try these questions. Try them all if you want to. Questions 2, 3 and 4, then 7, 8, 9, 10 and 11. And check your answers regularly after every single question you attempt to make sure you're on the right lines and not making any silly mistakes or getting yourself confused. And if that is the case, and ask me, I'm here, that's what I'm there for, or even leave a comment in the comment section. So thank you very much for listening again. Please do subscribe, and I'll see you in class, or if not in class, on an email or the comments. So take care, and I hope to see you all soon. Goodbye for now.